In the last segment, we discussed that Bohr assumed that every atom has a non-radiating stationary state, but that even though there are non-classical state, the orbits of the electron can be derived using classical mechanics. Let's see how that works, how the two things can come together. So let's take, this is our nucleus, and let's consider some electrons going around the nucleus in some circular orbits. So let's consider one electron. So, and let A be the radius. So this is our nucleus, and this is our electron. There could be more than one electron, and this is the radius, and this is the orbit. So we are assuming two things. One is that the nucleus has infinite mass, and that the orbits are circular. That is, they are not elliptical. You can consider the case where the nucleus has finite mass, as well as where the orbits are elliptical, and it's not very difficult, but this is kind of a simplifying assumption so that we have a more straightforward derivation. Let's set up the equation. So our fundamental equation is force is equal to ma. Here the force is the electrostatic force. So let's assume that our nucleus has, the atomic number is Z. So the nucleus has charge Ze, and then the force felt by the electron would be Ze squared divided by A squared. So this is the electrostatic force on the electron. And let's assume that our electron is, whizzing around with some velocity v. Then it's the centripetal force is given by mv squared divided by A. So this, we can say equation number 1. So from this, we can figure out what the kinetic energy of the electron is. Half mv squared, and then Z. So from here we see that from the left hand side, we multiply it by say 2, and then we divide by 2 and multiply by A. So then we get half mv squared is equals to 2A. So this is our kinetic energy. Now, Bohr introduced the quantization condition from some more general grounds, and the quantization condition he introduced was in the following way. He assumed that the angular momentum, of the system was quantized in units of h by 2 pi. So what he said was that if the angular momentum is, so what is the angular momentum? It's the linear momentum times the distance from the center. So that is equal to some integer times h bar, where n is a positive integer. Well, it's actually a natural number, and h bar is h divided by 2 pi. So this is known as h bar, sometimes also known as Dirac's h, but yeah, these days people just call it h bar, or sometimes called rationalized Planck's constant. From this relationship, we can derive a quantization condition. We can express the speed or the modulus of the velocity, instantaneous velocity, as h bar divided by ma. Now we can use this to eliminate the velocity, say, from this equation. And if I do that, then it's just a one line of algebra. We get a solution for A in terms of this new integer, n squared, h bar squared, m z e squared. But because n can only take, is a natural number, therefore A can only take discrete values. So this gives us a discrete quantized orbit. So this is the relationship which gives us quantized orbits. Now, for the hydrogen atom, and a lot of the experimental results that people were trying to explain revolved around the spectrum of the hydrogen atom, because it's the most simple atom we can have. So for the hydrogen atom, we have Z equals to 1. And if we now look at this expression and look at the ground state energy, which is n equals to 1, so that should be A1, but somehow it's called A0. So A1 is actually A0. And then we get h squared divided by m e squared. So this is the, so to speak, the radius of the hydrogen atom when the electron is in the ground state. And if you plug in these values, then A0 turns out to be 0.528 into 10 to the power minus 8 centimeter. This is sometimes known as an angstrom, but these days angstrom is no longer used. So now that we have a quantization of the orbits, we can find out the quantized energy levels for the hydrogen atom, or for any atom which has circular orbits in general. It'll only be very accurate for the hydrogen atom. So the total energy would be given by the kinetic energy plus the potential energy. And the kinetic energy is, as we derived before, it's ZE squared divided by, say, 2A. And the potential energy is given by ZE squared by A. So here we are using the CGS unit. And that's why in the Coulomb's law, from which we derive the potential energy, the constant K is set to 1. Otherwise, you'll have like 1 over 4 pi, epsilon naught, and stuff like that. So, okay, so we can simplify the energy now to be minus ZE squared by 2A. Now, if I put in the quantized value of A that we derived here, so here we derive the quantized orbits. So if we might put that into this expression, we get the energy levels, quantized energy level, and that's going to be mz squared e to the power 4 by 2 n squared h bar squared. And so this was a very successful and famous formula that Bohr derived using the two assumptions that we discussed.